Hello everybody. In this video we're going to be talking about measures of center of a data set. There's a few ways we can talk about data sets, some things we want to describe about them. One of them is where their center is, and another one is how spread out they are. In this video we're talking about where their center is. Now we've already touched on one of these, that is the median, or the second quartile, same thing. And we talked about that in a previous video, so please refresh your memory on that, watch that video if you haven't already. In this video we're going to be talking about mean. Okay? So, and then we'll talk about the relationship between mean and median. How are they similar? How are they different? Okay? So, let's talk about the mean here. The mean is one way to measure the average value of a set of numerical data. And here we have the formula, a formula for the population mean. I have written here the Greek letter mu, mu is how it's spelled in English. The Greek letter mu on the left-hand side equals sigma x over n. Sigma, that capital sigma, means to add up whatever's to the right. So in this case, we're adding up the data values of x. Sigma stands for sum, S-U-M, and in mathematics, sum means to add up. Sigma being the capital Greek letter for S. All right, so we're going to add up all the data values and divide by n, which is the population size. That's the total number of data values that there are. So add up all the data values, divide by how many there are, and that gives you the mean. This is called the population mean. We can also talk about the sample mean. Right? The sample mean has exactly the same formula. We add up all the data values and divide by how many there are. But in this case, we're thinking of the data as coming from a sample instead of from the whole population. So it's exactly the same formula. If you know how to do one, you know how to do the other one. Why are we giving them different notation like this? Well, because we're going to be talking about these differently. We're going to be comparing the population mean to the sample mean. So we need to think about these a little bit differently. Even though they're computed the same way, they really come from different data sets. And so their values may be different just because the data we're using is different. Notice that the sample mean is an x with a bar over it. All right, so it's read x bar. X bar is the sample mean. Okay, and so what we're going to do is we're going to do a couple examples of computing these. We're going to compute the mean of a data set, and we're going to compute the mean of a frequency distribution. Okay, so here we go. Let's compute the mean of this data set. All right, so if you remember, the formula was, oops. If you remember, the formula was mu equals the sum of the data values divided by the number of data values, right? So we just add all those data values up, 2 plus 6 plus 7 plus 8 plus 2 plus 3, and we divide by, how many of them are there? There's 6 of them, okay? So let's add up that numerator. We get 28 over 6. Make sure when you do this on a calculator that you do the numerator first before you divide, right? If you just type all that in and hit divide, you may get the wrong answer. Make sure you finish computing the numerator first. And what we get here is approximately equal to, I'm going to round to 2 decimal places, 4.67. So 4.67 is the mean of this data set. All right, let's go to the next example. Compute the mean of the distribution given below. So now instead of giving you the data set, what we have here is we have a table describing the distribution of data. We can resurrect from this the data set. So let's go ahead and do it this way. We will learn below a quicker way to do this, but let's do it this way. Let's reconstruct the data set and then compute the mean using the formula that we just used. And at the end of this video, you'll see a quicker way to do this. Okay, so the data set, what does it say? It says we have a data value of 4, and the frequency is 1. So 4 occurs once in the data set. So that's a 4. And then we have a data value 5, which occurs 3 times. The frequency is 3, so it occurs 3 times. Then we have data value 6, which occurs twice. And then we have data value 7, which occurs once. So this is the data set. So if we wanted to compute the mean, let's use the other notation this time. Let's imagine that this data set was a sample. Then I would be computing, the notation I'd use for the mean would be x bar. And we know that we do the sum of the x's divided by the sample size. Same formula as before, just different notation. So the sum of the x values, I just add all these up. Divide by the number that there are. There's 7 this time. And the numerator comes to 38. The denominator is 7. If I do that division, I get approximately 5.43. So that's the mean of that distribution, or of this data set. All right, so that's the mean. That's how we compute the mean. How do we interpret the mean? What does it mean to us, right? So here's a couple ways to interpret the mean. The mean represents a numerical average of the data. In some sense, the average is a single number which best represents the data. Another way to think about it, though, is that it represents a balancing point of the distribution. So if we take this distribution we used in an example in the last video, where we made a dot plot to represent the distribution of numbers. And we can imagine that these dots were actually had mass, that they actually weighed something, and they were sitting on a plank, right? This black line is a plank. Then the mean is exactly where you would have to balance that, where you would balance that plank so that it doesn't tip one way or the other. So it has this very nice geometrical interpretation, in that the mean is the balancing point of a distribution. Now compare that to the median. The median is the value that splits the data in half. It's the value, it's the middlemost value. So notice that the mean and the median are not necessarily the same. And in this example, with this distribution, we can see that they are somewhat different. Now, why is the mean pushed further to the right here? Why is the mean a little bit greater than the median? Well, if we think about this idea of it being the balancing point, this makes sense because we've got some mass way, way out here on the end of this plank, right? And so you know that if you hold something out very far away from yourself, it has more influence, right? So if I take an object like this bowl and I hold it close to me and lift it, it's not too hard to lift. But if I hold it, if I stretch out my arm and hold it very, very far away from me, it feels a lot heavier. It has a lot more, it takes a lot more effort to lift it. So it has more weight to me the further it is away from where I'm moving my joint, right? Well, the same thing here. These data points that are very, very far away, as far as the mean is concerned, have a lot more weight than the data values that are nearby. And that's why the mean tends to get shifted over when we have these extreme data values. Notice that the median isn't going to care so much because the median splits the data exactly in half. Let me show you another illustration of this fact. All right, so here we have, let me zoom in a little bit. Here we have some data points. All right, I just got a bunch of data points. And from these data, I have made a box plot. All right, so if you see, if I move these data around, it changes the shape of the box plot. Now remember, the middle line in the box plot is the median. Right? So I can see that the median is right here at 1 right now. Now what happens if I take one of these data points and drag it out away from the rest of the data? Notice that the median is not changing. Right? The median stays exactly where it was. But the mean down here, this little red number, is changing. So the mean is heavily influenced by the position of this one data point. But the median does not care. right? I move other data values around. The median will move. It will move, but it's not as heavily influenced by extreme values as the mean. And so this is something we want to keep in mind when we use means and medians. Which one, the fact that the mean is so heavily influenced by these data values tells us when it may be appropriate or inappropriate to use it. So just in summary, the mean is the balancing point of the distribution. The median is the middlemost value of the distribution. So let's look at some examples where we have to decide which one to use. Should we be using the mean or the median in these cases? All right, so let's go over to the whiteboard. I've got this over here. Okay, so here's our example. John is considering applying as an assembly worker at a large factory. He would like to know how much he might expect to earn as an employee there. Which measure of average, mean or median, would better represent his salary? So to think about this problem, let's imagine the salary of all employees at the factory. All right? So here's 0, and then the salaries go up. So assembly line workers might have earnings down here, right? Assembly workers, relatively low salaries, right? They're all, a whole bunch of them. You're going to need a lot of those at the factory. And then we got maybe some managers over here. And then we got the CEO over here. So looking at this picture, what measure of average would best represent John? Well, if we think about the mean, what would happen with the mean? Well, we talked about how the mean is influenced by outliers, right? Data values that are quite large. So this CEO's salary and these manager salaries are going to influence the mean, right? So when we go to compute the mean, it's probably going to be situated somewhere over here. Okay, the mean, mu. Now what about the median? Well, the median cuts the data in half. Now there's so many assembly workers over here that the middle value is going to be somewhere in there, right? So the median is going to be somewhere in here. So which value is a better value for John? Which one would better represent his salary as an assembly worker? Yeah, the median, right? The median would better represent John's salary because it's not influenced heavily by the CEO's salary and these managers' salaries. So the median is the best measure of average in this particular situation for John. Okay, let's take a look at another example here. Example number 2. Ben works in payroll at the factory. His boss asks him how much the company spends on employee salaries. Should he use the mean or median to determine an answer for the boss? Okay, let's think about this. Well, for payroll, you want to make an account of everybody's salary, no matter how extreme. Every dollar matters, right? You don't want to just represent the bulk of employees. You need to represent everybody. So in this particular setting, including the CEO's salary and the manager's salary is important, right? So here would be a case where the mean would be the better measure of average. You don't want to gloss over those other salaries if we're if we're doing bookkeeping. Okay, so when you're choosing the mean or the median, If you want to minimize the effect of outliers, extreme data values, then you would definitely want to use the median instead of the mean. If it's important that you consider all values, including outliers, then use the mean instead of the median. And typically we should be very cautious of using the mean if the data is skewed. Because if the data is skewed to one side, if there's lots of large values as opposed to small values, or lots of small values as opposed to large values, then the mean is going to be influenced a lot by that. Whereas the median isn't influenced so much by that. All right, and finally, the last topic here is the weighted mean. Now, the weighted mean, we actually already discussed this today. It was the second example that we did. But let's just see how this plays out. Here's a formula for it. The weighted mean is given by the sum of each data value, x, multiplied by its weight. And then we divide by the sum of the weights. So this is useful if we want to treat some values as being more important or having more influence in the data than other values. All right? And that influence is what we're calling weight here. So let's take a look at this example right here. Okay, so here we have the grades, right? So we have the different grades, and we have different weights for the grades. Notice that homework and labs are weighted at 20%, writing assignments at 20, and exams at 30. They haven't taken the final exam yet, so we're not going to include that. Okay? So let's compute Amy's weighted average. Okay? So let's go look at that formula for weighted average. The formula says it's the sum of each data value times the weight divided by the sum of the weights. Okay? So let's go ahead and do that. So we're going to take each data value, which for Amy is her scores. So that's going to be 92. We're going to multiply it by the weight, which is 20. And then we add these up. So then we do her 86. Multiply that by that weight, which is 20 again. And then we do 77, multiply it by that weight, which is 30. Okay? And then what do we divide by? The sum of the weights. So 20 plus 20 plus 30. And what does this come to? So this is equal to, the numerator is equal to 5,870, and the denominator is equal to 70, right? And so when we compute this, we end up with 83.86. Okay, so that's Amy's weighted average. Now let's do Bob's weighted average. So for Bob, we do his first score, 82, multiplied by the weight, 20. His next score, 93, multiplied by the weight, 20. And his last score, 83, multiplied by its weight, 30. And then we divide by 20 plus 20 plus 30, the sum of the weights. Okay, this is equal to 5,990 divided by 70, which is approximately equal to 85.57. So Amy's weighted average, Bob's weighted average. Who did better overall? Just slightly, Bob did. Okay? So this is how we do a weighted average. And I want to point out, as I said earlier, that we actually did a weighted average at the very beginning. All right, so we're going to come back up here and do this example of computing the mean from a distribution using the notion of weighted average instead of the way we did it the first time. Okay, and you'll see it's a little bit quicker, but it's really the same thing. So let's do this over again. Let's erase what we had before. And what we're going to do here is we're going to note that the distribution here, the frequency distribution, is actually giving us weights associated with each number. The data value 4 has weight 1. Data value 5 has weight 3. 6 has weight 2. And 7 has weight 1. So if we do a weighted average with those weights, we will get the mean of the distribution. So that's another way to think about the mean, is that it's the mean of it's the weighted average of the frequency distribution, where the weights are the frequencies. So let's go ahead and do that. So the weighted average here, is going to be equal to, well, we remember the formula was the sum of each data value multiplied by the weight divided by the sum of the weights. So the first data value is 4, and its weight is the frequency, which is 1. The second data value is 5, and its weight is 3. The next one is 6, and its weight is 2. And the next one is 7, and its weight is 1. All right. Now what's the sum of the weights? Well, that's 1 plus 3 plus 2 plus 1. And notice what we get here. We get 38 over 7, which is what we had before. So we're really getting the same thing. We're getting the mean, and that is approximately 5.43. The same answer we had before. But I hope you can see that this will, in general, be a lot quicker than reconstructing the data set. Sorry, let me move out of the way here. You may not be able to see that last answer. This is a lot quicker in general than recreating the data set, especially with bigger data sets. With bigger data sets, the frequency distribution will be a much more efficient way to summarize the data than just looking at the data set on its own. And so this will be a much quicker way to compute the mean. Okay, so that is it for this video, and I hope you learned something, and I'll see you in the next one.